All right, so I'll try to finish this lecture. If time is up, I might ask you to stay for a few minutes just to finish it so that we don't fall behind as the semester is ending. If you have your fact characterization extra credit, give it to me. If not, you can turn it in anytime on Friday, doesn't matter. There is another extra credit opportunity on Canvas for +5 if you'd like. It's not mandatory, but it's on proteins. You'll find it in this week's on modules. Okay. You can give it to me next week, anytime, doesn't matter. I'm not going to give you deadlines. On your own good time, you can give it to me if you want extra credit. All right. So just recap. I know you're tired, especially Wednesday lab group. But bear with me 20 minutes, 25 minutes. Just to bring back what we talked about, let's just have a breathe and relax and try to remember protein separation a little bit. Why do we care about protein separation? Where do we use it? Yes, is that to you? Yeah. To determine nutritional properties, nutritional quality. Yeah, so we isolate to characterize the protein, nutritional quality, functionality, enzyme activity. But what else? Not an exam, sorry. Yeah, production of protein, concentrate and isolate. Anything else? Yes, Laura? Say that again? Yes, so production of protein, concentrate and isolate, purification of enzymes for assays, purification of substrates for enzymatic assays. So these kind of applications. For isolation to determine impact of processing on proteins. So if we have certain flour and it's being processed to activate enzymes, like in soy flour, for example, it's heated to inactivate trypsin inhibitor. So what happens to the protein after that process? So to isolate, characterize, and determine impact of processing on the protein. Okay. What are some of the methods we talked about for separation, Ellery? Salting out is one. Great. Page?
Hydrophobic interaction.
Hydrophobic interaction, chromatography. Caitlin? Solvent, using solvent to precipitate our protein. Grace? Protein denaturation by thermal treatment. Yes, I saw another hand up somewhere. Go ahead, Dora. Okay, yeah, protein denaturation is correct. So chromatography, separation by size, separation by adsorption, depending on charge. I think we were talking about separation by size using membranes. So let's just go back to review that. Oh, I need to go to the right screen. Okay, so that was the last slide I showed you, and it was a little bit rushed, so I want to go back to it a little bit. And separation by size using membrane filtration. So here we have different techniques that we use either on a small scale or a large scale. So if we are working in a lab on a small scale and we want to separate proteins based on size from other constituents that could be smaller in molecular weight, for example. So we use centrifuge tubes that are special centrifuge tubes that have membranes in the middle of them. And these membranes have different pores. And the size of the pore can be controlled. So you can buy tubes with membranes that have different pore sizes. So very common is the cutoff of 3 kilodalton or 1 kilodalton. These are very common to kind of move salt or small sugars or small molecules. By centrifugation, the small molecule will be passed through, and then your protein will be in the dentate, which is the upper part of that tube. So this here you apply centrifugation, apply pressure to force the permeates, to force permeation through the membrane pores. Okay, so this is really small scale, lab scale. We can go a little larger scale by using, still benchtop, but using a membrane system where you have a pump, sheets of membranes, sometimes you use double sheets of membranes. And what happens, you have your solution here with proteins and sugars and small molecules that you'd like to separate from the protein. So the pump is used to pump them through the filter paper or filter membrane, sorry. And what happens is also the permeates are collected in the back here containing small molecular weight components you don't want in your protein when you're purifying your protein. And then the rest of your components, including proteins, the large molecules that is, will go back to the original flask. And it's kind of like a cycle, and you do several washes to make sure that you purify your protein. So also the size of the pore size of the membranes can be controlled. Now, depending on the size of the pores, you can have microfiltration, ultrafiltration, nanofiltration, or reverse osmosis. So here's a table that kind of summarizes the separation based on the particle size itself, the molecular weight, the characteristics of the particle. So if it's very, very small, it will be ions. And then if they're a little bigger, there will be molecule, macromolecule, and cellular, like bacterial cells, for example. So what happens here, basically you start with microfiltration. This kind of takes care of filtering out bacteria, let's say. And then, or fat globules. Bacteria, fat globules, these small. And ultrafiltration, that's mostly your protein will be in the retain phase or retained, don't go through the pores. Nanofiltration, basically some molecules here, like lactose, vitamins, maybe. Reverse osmosis, you can get rid of ions, salt, basically. So this is kind of an illustration. If you use microfiltration, your fat globules and bacteria will be retained. They don't go through. And then protein, lactose, minerals, water, all goes through here. Ultrafiltration, proteins are retained, they can go through, but lactose, minerals, water. This is the milk system, by the way. I forgot to mention that's milk system. If I apply nanofiltration, then lactose is retained. We can get the lactose purified. Minerals and water will pass through. If I want to purify water now, I can use reverse osmosis and filter out the salt. And then I get purified water. So these are the different types of membrane based on the pore size. So you can use chromatography to separate by size as well. We often use that as a bulk preparatory step in the lab, where we want to separate proteins from other molecules and sometimes separate proteins themselves based on their size, large molecular weight from smaller molecular weight proteins. So this is kind of a reminder to you. We covered this in chromatography section. The size exclusion is also referred to as gel filtration and gel permeation. So both terms are the same as size exclusion. Basically, it's just different terms. But again, here, large molecules don't go through the pores of the different particles. They migrate with the void volume. So they elute first, and the small particles go through all the pores and get delayed. Then they will be used later. So basically separation on side. And when we, just a reminder that when we pick our size exclusion chromatography, there's so many different kinds we can pick from, depending on the particle size as well as the pore size. So you can select different particles and different pore sizes based on the range of molecules you have and you want to separate. All right, let's think about this together in a simplified manner. So here you have a mixture of proteins and you want to isolate them, separate them from each other. So here the question says, you have protein X has a molecular weight of 90 kilodalton. It has a net charge of +5 at neutral pH. And you want to separate it from protein Y that has molecular weight of 30 kilodalton, same net charge at the same pH, and a third protein that has molecular weight similar to X, but has a +2 net charge at, again, pH 7. Which of the following do you think would work best? Oh, Tyler, you have an answer right away.
I think maybe A and C.
A and C. Let's give the others a moment to think about it and see if they want to choose the same answer or something different. Ellery?
I was going to say C.
You were going to say C.
I didn't read all of C. I say C.
You also agree with Ellery then. C. Last answer. This is your last. If you're going to win $1 million, that would be your last. Okay.
But you would get a lifeline.
Huh?
You would get $1 million. You get a lifeline.
Do you want to get a lifeline from anybody? Call a friend? I think you should call a friend. Anybody else? Caitlin?
Is it all of the above?
Yes. It is all of the above. You lost $300. Okay, so it doesn't matter the order. Okay, so whether you start with cation exchange first or size exclusion first, it doesn't matter. You can start with either. So you can separate based on charge. They're all positive charge. So you want to go for cation exchange at pH 7. So there you can do cation exchange. So what you separate in this case is X and Z from Y. They get separated. Y has a very different molecular. Okay, then you have X and Z that have very close molecular weight. So you can separate them by cation exchange. So if you choose size exclusion first, then you are getting X and Z, and then you are getting protein Y separate. If you choose cation first, you get X and Y together and Z separated because it's +2 net charge. Doesn't matter which way you want to go, it's A or C. Either way is fine. Now B, does it work? Precipitation using ammonium sulfate. Yes, it does work because then you can add a little bit of salt. Protein Z is going to precipitate because it has lower net charge than Y and X. Of course, it's simplified. You need to know what concentration you want to use to precipitate out this and keep X and Y in solution. You centrifuge, you have X and Y in solution, and they are very different in molecular weight. You can get the cutoff, kilodalton cutoff of 35 or 40 kV. Then the 30 kilodalton protein, when you centrifuge, kind of go past the membrane pores, whereas your retentate will be your protein X. Yeah, so all of these work. Okay, so next is electrophoresis. So we don't get a chance to do a lab on that, but some of you are already familiar with that from a research lab. But basically, electrophoresis is also can be separation by size or separation by charge to size ratio, or just separation by charge, isoelectric focusing, which I'll talk about next. So you can have STS page. STS page means sodium hydroxyl sulfate polyacrylamide gel electrophoresis. So polyacrylamide. So your polyacrylamide is forming your gel. And depending on the concentration of your polyacrylamide, you get different pore sizes of the gel. And the SDS, what the SDS does is interacting with the protein, it breaks down non-covalent interactions. So if you have protein-protein interaction by hydrophobic bonding, hydrogen bonding, or ionic bonding, these are broken by SDS, and the entire protein becomes negatively charged. Do you want me to repeat anything? I can.
You said it breaks all non-covalent bonds.
It breaks all non-covalent bonds. Basically, it denatures the protein. And it causes the protein to be negatively charged. So now all of your proteins are negatively charged. And then when you run, you put them on a gel and you run a time, they're all going to move in one direction. So they're all going to go from negative to positive because they're negative. So they're all going to go down through the gel and separate based on size. Because the gel has particular size based on percentage of the protein. So the urea gel is basically, the urea also denatures the protein, but does not necessarily give the protein charge. So the proteins will then separate, also using polyacrylamide gel, but separate based on charge to size ratio. So the charge is taken into effect, not only size. The native phage is not very much used because of the proteins in nature. They have quaternary structure, most of them. Very minimal types of proteins are monomers in nature. So it's very hard to see the proteins on a gel that you don't do anything to it. You don't denature any of the interactions. So native, that means you don't have any detergent, you don't break down any interactions, and the proteins migrate based on their charge, their size, and they can be polymers because you didn't break any bonding. It's really hard to see any differences. If you want to see impact of processing or thermal treatment, you won't be able to see much if you run a native phage. So basically, this is not done very much. Mostly you'll see SDS or urea phage. So basically, I have a demonstration here. This is a gel that has expired. That's why I'm using it. If it expires, then the gel inside might have shrunk, the pore size is different, won't be good to run anymore. The gel just dried out. There's a piece of gel right there. Okay, so, oh boy, that's not the gel I wanted to show you, but anyway, there is a kind of a comb. This green thing is a comb, like to brush your hair with, but usually you have multiple wells. This is a one well comb gel used for different purposes. But usually you have like the comb, and then you have multiple wells. And then what you do is you fill the chamber with a running buffer, the buffer that you use for running a current through your gel. So you have a chamber and you fill it with your running buffer, where there is a running buffer line. And once this is filled, then you put your gel in there. Make sure that you have running buffer in this little chamber as well. And then using gloves, not with your bare hands, you remove the comb. Your bare hands have protein. So if you don't use gloves, you have a phantom band that is coming from your hand. So you just remove the comb and then you use your pipette to load certain microliters of your sample in each well. So once that happens, well, I'm just going to remove this, pretend that I have, so that's your comb. And then you put this on and then you run a current. You basically connect it to a voltage source and then you run a current. So what happens is you always run a standard that has been stained before, prior, it's because your protein is not stained in your sample. So you can see your molecular weight marker going down. We can see the front because you have usually Comasi Lamely buffer. The Lamely buffer has a color, so you can see it go down, and then you stop it when it reaches the bottom. Well, one thing you don't want to forget doing is removing that strip. Otherwise, you won't be able current to run through. I've done that before. Loaded on my sample and nothing went by because I did not remove this. So when it's done, this is convenient to be made in such a way that you can put your and you break it open. So you break it open just like that. Basically, this is moving out the four steps. Just in case you're curious. Okay, you break it through. See, this is the shriveled old gel. And then gently, you take the gel out and you place it in a staining Comasi glue stick. So the Comasi glue is going to react with your protein and it's going to give you a band that you can see. But you cannot see it like that because when the gel comes out of the stain, it's all dark blue. So what you need to do is destain it. So you destain it in a specific solution or water, depending on what you use for staining. And then you image it like that. And then you see the proteins bands. This is soy protein extracted from soy flour. And then you can see in soy protein, you have different types of protein bands that are different in molecular weight. You always run a molecular weight marker. Now, one thing about acrylamide is its parsimony. So I'm holding it in my hand. You want to hold it? Don't hold it. Why? I don't care. I do care. When acrylamide is a gel form, it's no longer a parsimony. If it's in a powder form or liquid form, you have to be very, very careful. So nowadays you can buy these pre-made. Back in my time, over 25 years ago, I had to make them myself from powder acrylamide. So that was super scary. But now it doesn't matter. You can touch them with your hand. They're not carcinogenic because they are gel. So there you go. You're good at electrophoresis now. The other type of electrophoresis is isoelectric focusing, where here you separate based on charge, basically. So what you do in this case is you get another strip, also an acrylamide, the gel strip. But what you do is before you run your sample, you build a pH gradient. So how do you build a pH gradient? You use electrolytes, which are polymers or molecules that carry a lot of charge, different not negative charge. Then you load your electrolytes and you run a current. So these electrolytes are going to separate based on how much charge they carry, and those that are negatively charged will go towards the positive charge of the electrodes, and then those that are positively charged will go to the negative, and then you build a kind of a pH gradient. Then you load your sample, and the sample migrates until it reaches its isoelectric point. So when it reaches its isoelectric point, time's up. When it reaches the isoelectric point, it precipitates sediments. And then you stain the same way, and then you can see your spots. I'm going to finish electrophoresis and let you go, guys. I'll finish the rest of this lecture on Friday. Okay, so you can run 2D electrophoresis. You can separate first based on charge. Oh, and that was the purpose of having one well, because you take that out and then you place your strip that you already separated the protein, you place it here, and you would have a gel that you would run based, and then you get separation based on size. That's the purpose of having only one well, is to have done the the isoelectric focusing first, and then you put the strip here, you run the current, and then the proteins migrate based on size. Obviously, the strip will have to be treated with STS or urea so that the protein migrates based on based on size. So what you can see here, we have two separated proteins. When we run them on the gel, they have similar molecular weight. So if we didn't do the isoelectric focusing, we'll get both proteins here, and we won't be able to see them as two separate bands. In this case, this band gave you two different molecular weights. So this illustrates that 2D electrophoresis helps with better separation and see more protein bands. It has an impact. For example, when I talk about immunoassays, I'll show you in Western blot how important this separation is when you're detecting allergens, for example. So it's really important to do 2D electrophoresis when we're doing immunoassays, for example. Thank you for staying 5 minutes. Sorry, Wednesday group, and I'll see you on Friday.
So I gave you yeah. So
What's that?
how'd you crack it open on the lid? Everyone uses a knife.
Probably.
Wow.
Yeah, you just put it like that and push it in.
Oh.
Huh. Now,
And then use a spatula or the little tool that comes with
this
it
is
for that.
exactly.
Because every time that I went to learn it, it just is too stressful to me to do it on the corner. Like everyone I see. I mean, you can totally do it. I know
Yeah,
it
you
said
can.
to in SOP. I know some people did before me, but
Yeah, I always do that. It's very easy. Just press hard down and press hard down. Not too hard to break the gel, but just hard enough to crack, to hear the crack.
I like the time. That's my baby.
For the last question, do you want a description of the method or you just want the method and then why?
Can I say this?
It says, if you ask for a method to analyze protein fraction, it said, what would you answer?
Yes, exactly. Only the method and then how we do it.
Okay.
We're not.
How would not, you don't need to explain why. You just
No,
say,
no, just it, but how do you validate it?